righty. It came to my attention that we need to put a little bit of time into parametric and vectors and the difference between the two, or there's not much of a difference, but the words are important. So if things didn't go well for you on the practice exam, don't feel like the world is over. I need to go, let me know what I need to go over. And one of them is this right here. So a lot of you were thinking about slope when you were supposed to be doing speed. So there's a difference between slope, a velocity vector, and speed. So speed is the length of the velocity vector. It's the distance. You're going to have a two-dimensional velocity vector, and you are looking at it is equal to some x prime function and some y prime function. So if I need to find the length of that vector, and I know its horizontal and its vertical component, then I'm just going to apply Pythagorean theorem on it. And it's straightforward, but you have to be aware of which formula to use. Then if you are asked for the velocity vector, then you are keeping the x prime and the y prime as two separate functions. And writing it in the pointy brackets. If you're asked for slope specifically, it is always dy over dx. And whether you're dealing with polar or parametric or vector, it's always dy over dx. When you're given a parametric or a vector function, you have those two separate x's and y's already with respect to time. But if it's polar, you have to convert it using the polar formula. So you will be given some r with respect to theta. You'll substitute those r's with whatever that function is with respect to theta, and then you're going to find the derivative of the y with respect to theta, the derivative of the x with respect to theta, just like as if it were a parametric slope. Now, if you have to do concavity when you are working with parametric or vector for that matter, you have to do a little bit extra, and this is a very, very specific formula. Realize that you have two functions with respect to time when you find your first derivative. When you find the first derivative of y with respect to x, these with respect to t's cancel each other out because you have two equations with respect to t. But once you have dy dx, you have one single function with respect to time. And I'm just going to put h of t to represent whatever function that is with respect to time. In order to get to the second derivative, I have to differentiate with respect to x in order to get that second derivative with respect to x. And the derivative of, so we get the second derivative. Now, over here, you're taking the derivative with respect to x, but your input variable is t, not x. So what you want to do is treat this as a baby function. You are doing chain rule. H is the mommy function. The derivative of h, so derivative of the mommy, shove the baby in, or give mommy her baby, if that sounds better, multiplied by the derivative of that baby with respect to whoever you are with respect to taking the derivative. And that's a really, really, really important formula. Not only is it important for finding concavity, but it's also important for anytime you do implicit differentiation, which I saw that was another issue, was just needing to practice implicit differentiation. Anytime you're doing implicit differentiation, so say, for example, you're differentiating with respect to time, and let's say you have pi RH. Let's say that's what you have. R and H are each, if they are variables, they have to be treated as their own function. Now, pi is a constant multiple, so you can pull it aside, and then you have to do a product rule on those two, but with respect to time. Now, if they're just sitting there like, hi, I'm R, take my derivative, then it's dr dt. And product rule says, take the derivative of one of them, but keep the other, plus reverse the process. Keep the r multiplied by the derivative of the other one. But we could also have issues where you're asked to take the derivative of, let's say it's r squared times h. Still need to do a product rule. But if what you are dealing with is more than just the variable itself, if that variable is inside another function, then you really need to think chain rule. And you need to look at it and go, all right, the product rule is derivative times keep plus keep. Why did I write equals? I don't know. I was about to draw two lines, so. So keep times and then derivative. Now, if it's just the h, again, it's just dh dt. But with the r squared, I look at it as bleh squared. Derivative is 2 times bleh. Give mommy her baby, multiplied by derivative of baby with respect to the time variable. So make sure that you feel good with implicit differentiation. Now, I need to come back over to that formula that we actually didn't finish, because that's not the formula. To save pain, instead of multiplying by this ratio, we divide by it. And then dx dt is something you had to have already found when you were taking that first derivative. So make sure you're clear about that formula. But that's if you need concavity. If you need acceleration, that's completely different. So what I want to really have you take a look at and study, if you don't already feel comfortable with this, when we're looking at functions more like with just, I've got an x function and a y function, we've got slope and concavity, the hard way, shall we say, rather than when we have just y equals f of x. Finding the length of a curve. The parametric formula is actually the easiest one, but do you remember the formula for length of curve if you have a y equals f of x? Uh-huh. And were you remembering it? Yeah. Yeah. So from x equals a to x equals b, square root of 1 plus the derivative of the function squared. But if you're dealing with parametric, length of curve, and I have alpha and beta here because I want to emphasize that it's with respect to time. Venemeyer and now.
Oh, right. My class wants to talk about classes and was like, let's keep learning calculus. Like, art or whatever.
Well, I'm recording.
I will try.
Yeah. So with respect to time, do you see that this actually is the same formula I just talked about for speed?
I'll probably be back.
Do you see that that's the same formula as speed? That's important to take note of. That is the same formula as speed sitting, what I should, actually, I just realized I didn't specify, inside the integral. And if you are dealing with two-dimensional motion, why would that be the same thing? So if you have some function from t equals alpha to t equals beta, but you're dealing with the xy plane, you don't have a t-axis. So that path right there is the actual path of travel. And anytime you want to know the distance you have traveled on a path, it is the integral of speed. And the formula for speed, when you are dealing with parametric motion, is this formula right here. Arc length and speed are the same formula when you are dealing with parametric motion. When you're dealing with regular old hi, I'm a y equals f of x function where the x is time, then they are different formulas. The arc length formula, if you're dealing with a regular function, goes back to this. If you are looking at y is a function with respect to time, and you're trying to find, hold on, my brain just all of a sudden went away. Come back, brain, come back. Okay, if you are trying to find the length of the curve that you see, and I'm putting a t and a y, if you are trying to find the length of this curve from t equals alpha to t equals beta, you're going to use this formula to find length of curve. But if you are finding speed when you are dealing with one-dimensional motion. One-dimensional motion where time is your input and you just have some output single number position. In that case, your speed is the absolute value of your velocity function, which would be the derivative. And in order to find distance traveled, you always integrate speed. Now I want to point out that f prime is representing velocity. If this is the position function, so again, just to emphasize, when you're dealing with a y equals f of t function, one-dimensional motion, arc length is different from distance traveled because you're warping the distance traveled with t by making that an axis. The actual motion is only going tra-la-la, la-la-la, just back and forth on a line. Now, another important thing that I saw was a problem. Total distance traveled and displacement. Sometimes they are the same, but sometimes they are different. If you want the total distance traveled, you are integrating speed. But displacement, so let's say this is the way I'm traveling. I travel from t equals alpha to t equals beta. The displacement is the straight up distance between the 2 points. And if you need to know the magnitude of the displacement, it's a nice big bowl of work. You've got to find what is your change in x, the horizontal. You've got to find your change in y, the vertical, and then Pythagorean theorem, the two of them. So just take a good look at the difference between those. And I feel like that covers basically what I wanted to talk about with really recognizing the difference of parametric and vector motion. And I'm going to stop recording for a moment.